Minute 0, the world is calm. Minute 60, everything has changed. This is a hypothetical escalation timeline, for education, not instruction. This is a story of the unthinkable. A story of how our world, in a single hour, could unravel. It is a work of fiction, pieced together from declassified documents, scientific models, and expert analysis. The events described are not real, but they are terrifyingly plausible. The purpose here is not to incite fear, but to foster understanding. Only by grasping the mechanics of catastrophe can we hope to prevent it. We must look at the abyss to appreciate the ground beneath us. What does the first hour of a nuclear war truly look like? It begins not with a bang, but with a whisper. The clock starts now. We are at T-minus 60 minutes. A regional war simmers, rhetoric hardens, communications strain, perception becomes everything. For decades, mutually assured destruction, MAD, has deterred war by promising overwhelming retaliation. But peace on a knife's edge demands flawless information and near-perfect decisions. In this hypothetical, we follow minute by minute, from a small trigger to the brink. Leaders decide the fate of billions in less time than a pizza arrives. This is a sobering look at our most destructive creation, so we can avoid its final hour. The spark is almost invisible, a blip on a radar, a garbled transmission, a sudden silence on a routine patrol. In the vast expanse of the ocean, two rival destroyers shadow each other, their crews tense, every movement scrutinized. The air is thick with anticipation, as if everyone senses that something is about to go wrong. Suddenly, alarms blare. A sonar operator detects an unexpected contact, an unidentified vessel or perhaps a torpedo. The bridge erupts in activity. Officers bark orders, sailors scramble to stations, and the captain demands clarity. But the data is incomplete, the signal's ambiguous. Is it a malfunction, a decoy, or the real thing? In the chaos, a split-second decision is made. A defensive weapon is fired, intended as a warning shot, but it strikes a critical system on the rival ship. An explosion rips through the hull, sending fire and debris into the sea. The crew is thrown into panic, struggling to contain the damage and call for help. A frantic distress call goes out. Under fire, taking on water, request immediate assistance. The message is intercepted by multiple listening posts, some friendly, some not. In the confusion, the true nature of the incident is lost. Was it an accident or an act of aggression? The chain of command activates instantly. In a fortified command center, officers huddle around glowing screens, piecing together fragments of information. Protocols demand a rapid response, but the facts are murky. Each minute of uncertainty feels like an eternity. Military doctrine allows for a proportional response. Orders are relayed down the line. Prepare to launch conventional cruise missiles at the suspected attacker. Technicians input coordinates, double-check targeting data, and await the final command. The tension is palpable. No one wants to be the one who makes a mistake. Sleek cruise missiles roar from their launchers, streaking low over the waves. They are conventional, not nuclear, but the distinction is invisible to radar. On screens hundreds of miles away, the receiving nation's early warning systems light up with multiple inbound signatures. In a distant bunker, analysts scramble to interpret the data. The system cannot distinguish between a conventional and a nuclear strike in real time. The screens show only speed, trajectory, and impact points, enough to trigger the highest level of alarm. Ambiguity is now the enemy. Radar displays suggest a possible ballistic attack. Commanders must decide. Is this the opening move of a nuclear war or a tragic misunderstanding? The pressure to act is overwhelming. Action begets reaction. Each side believes it is acting defensively, but every move corners the other further. In the operations room, maps update in real time, and the faces of decision-makers are drawn and anxious. The world teeters on the edge, and the clock is ticking. As alert levels rise, extreme options are quietly unlocked. Nuclear launch protocols are reviewed, keys and codes checked, and the weight of responsibility settles on a handful of people. The line between caution and catastrophe grows razor thin. What began as a local accident is now seen as a possible strike on the homeland. News spreads through encrypted channels, and leaders are briefed in secure rooms. The sense of urgency is overwhelming. Every second lost could mean disaster. Heads of state and top generals face the same screens, the same incomplete data, and the same impossible choice. Wait for confirmation and risk annihilation, or launch on warning and risk starting a war by mistake? The fate of millions hangs in the balance. The debate is frantic. Advisors argue, intelligence officers plead for more time, and military chiefs warn of the risks. But the clock is merciless. Launch on warning procedures are reviewed, fingers hover over buttons, and the world holds its breath. Radars track every object in the sky, computers calculate arcs and impact points, but nothing is certain. The data is probabilistic, the consequences irreversible. In the end, the decision comes down to trust. Trust in machines, in people, and in judgment under pressure. Military doctrine recommends a full retaliatory strike. To hesitate is to risk losing everything. In these final moments, the world stands on the edge of the abyss, one misunderstood signal away from catastrophe. To truly grasp the gravity of nuclear weapons, we must first understand the science that powers them. Nuclear arms are not merely larger explosives. They are the product of decades of research in physics, engineering, and military strategy. Their destructive force is rooted in the manipulation of the atom itself, unlocking energies millions of times greater than conventional chemical reactions. At the heart of every nuclear weapon lies the principle of fission, the splitting of heavy atomic nuclei such as uranium-235 or plutonium-239. When a nucleus absorbs a neutron, it becomes unstable and splits into two smaller nuclei, releasing a tremendous amount of energy, additional neutrons, and gamma radiation. These freed neutrons can then trigger further fissions, creating a self-sustaining chain reaction. Achieving this requires assembling a supercritical mass, enough fissile material in the right configuration so that more than one neutron from each fission event causes another fission. The engineering challenge is immense. Early atomic bombs, like those dropped on Hiroshima and Nagasaki, used two main designs, the gun type, which fired one subcritical mass into another, and the implosion type, which used precisely shaped explosives to compress plutonium into a supercritical state. Both required sophisticated neutron initiators to start the chain reaction at exactly the right moment, maximizing yield and efficiency. Uranium-235 and plutonium-239 differ in their properties and handling. Uranium bombs are simpler, but require rare, highly enriched material. Plutonium, produced in reactors, is more efficient but more challenging to assemble due to its higher spontaneous fission rate, which can cause pre-detonation if not perfectly synchronized. The infamous Trinity test in 1945 was the first demonstration of a plutonium implosion device, marking the dawn of the nuclear age. Fission weapons are devastating, but the quest for even greater power led to the development of fusion, or thermonuclear bombs. These devices use a fission explosion as a trigger to compress and heat a secondary stage containing hydrogen isotopes, deuterium and tritium. Under these extreme conditions, the nuclei fuse, releasing even more energy in a process akin to the reactions that power the sun and stars. The engineering of a thermonuclear weapon is a marvel of precision and complexity. The Teller-Ulam design, used in most modern warheads, separates the fission and fusion stages with radiation-driven compression. X-rays from the primary fission explosion reflect and compress the secondary, igniting fusion fuel. This two-stage process allows yields from hundreds of kilotons to multiple megatons, thousands of times more powerful than the bombs of World War II. Over the decades, nuclear testing has revealed the staggering effects of these weapons. From the deserts of New Mexico to the atolls of the Pacific, hundreds of tests have illuminated the physics of blast, heat, and radiation. The largest ever detonated, the Soviet Tsar Bomba, yielded over 50 megatons, its fireball visible from hundreds of kilometers away, its shockwave circling the globe. The destructive power of a nuclear weapon is measured in kilotons or megatons of TNT equivalent. Hiroshima's bomb was about 15 kilotons. Modern strategic warheads often exceed 300 kilotons, and some Cold War designs surpassed a megaton. The yield determines the radius of destruction, the intensity of thermal radiation, and the scale of fallout. Delivery systems have evolved alongside warhead technology. Early bombs were dropped from aircraft, but today's arsenals include intercontinental ballistic missiles, submarine-launched missiles, and cruise missiles. Each system is designed for speed, survivability, and the ability to penetrate defenses, ensuring the threat of retaliation remains credible. The effects of a nuclear detonation are multifaceted. First comes a blinding flash, brighter than the sun, followed by intense thermal radiation that can ignite fires and cause severe burns miles from the blast. A supersonic shockwave flattens buildings and infrastructure, while prompt radiation delivers lethal doses to anyone nearby. Fallout is the lingering hazard. Radioactive debris is lofted into the atmosphere, carried by winds, and deposited over vast areas. Fallout can contaminate land, water, and food supplies for years, causing acute radiation sickness and increasing cancer risk for generations. The pattern and severity of fallout depend on the weapon's yield, altitude, and weather conditions at the time of detonation. The biological effects are equally dire. High doses of radiation destroy rapidly dividing cells, leading to burns, organ failure, and death. Survivors face increased risks of leukemia, thyroid cancer, and genetic mutations. Even low-level exposure can have lasting health consequences, especially for children and pregnant women. The environment suffers as well. Soot and dust from burning cities can rise into the stratosphere, blocking sunlight and disrupting global climate, a phenomenon known as nuclear winter. Even a limited exchange could lower temperatures worldwide, devastate agriculture, and threaten billions with famine. Over time, international treaties and test bans have sought to limit the spread and testing of nuclear weapons. Yet, the knowledge and materials remain, and the risk persists as long as these arsenals exist. Understanding the science is not just an academic exercise, it is essential for informed debate and responsible policy. In summary, nuclear weapons harness the most fundamental forces of nature, fission and fusion, to unleash destruction on a scale never before seen. Their effects are not limited to the battlefield, but ripple through the environment, societies, and generations to come. The Science of Starfire is a warning as much as a marvel, reminding us of the responsibility that comes with such power. With this deeper understanding, we return to our timeline, where every minute counts, and the consequences of misunderstanding the science could be catastrophic. The decision to retaliate assumes the data are correct, but what if they are not? In 1983, a Soviet satellite reported 5 American ICBMs. Lieutenant Colonel Stanislav Petrov judged it a false alarm, and was right. Sunlight reflecting off high clouds fooled sensors. In 1979, a training tape simulating a Soviet strike was fed to live NORAD systems. Jets scrambled before the error was found. We demand machine-speed accuracy from systems still vulnerable to glitches, and to human mistakes. Ultimate authority often rests with one person or a very small committee. Deterrence aims to prevent war, not fight it, by making the cost unacceptable. Second strike capability underpins deterrence, distributed across a triad: land-based missiles, long-range bombers, and ballistic missile submarines. Leaders see pre-planned options, from limited military targets to city-killing counter-value strikes. Orders move through secure, redundant channels with layered authentication to prevent unauthorized action. Cooperative safeguards exist, but once a lawful order is given, crews execute without the full picture. In our scenario, the leader chooses mass retaliation. The sequence begins. There is no turning back. Land-based missiles rise, then arc through space. Spacecraft on ballistic paths. Onboard guidance makes tiny corrections for pinpoint arrival. The initiator now sees the unimaginable. Their own launch-on-warning protocols engage. Hundreds, perhaps thousands of warheads are inbound. Deterrence has failed. The process is irreversible. On the ground, normal life continues. There are no sirens for a strike this fast. The first sign, a flash brighter than 1,000 suns. The hour is up. The immediate consequences are beyond comprehension. City centers vaporize. Blast waves demolish miles of structures. Continent-scale fires ignite. Medical systems vanish. Infrastructure collapses. Survivors lack food, clean water, and shelter. Millions flee shifting fallout. Soot lofted into the upper atmosphere blocks sunlight, nuclear winter, plunging temperatures and collapsing agriculture. The ozone shield erodes, ecosystems fail, famine threatens billions beyond the blast zones. A full-scale nuclear war could imperil human civilization itself. Yet we have stepped back before: test bans, non-proliferation, arms reductions. Verification, redundancy, and clear communication reduce risks. This is not only for presidents and diplomats. Scientists, engineers, and citizens all matter. We can be led by automated systems, or choose knowledge, foresight, and humanity. Choose de-escalation, diplomacy, and disarmament. Choose survival. The future is not yet written.